Okay, hello and welcome back. So today is part 6 of building an AI improviser in Max, and we are looking at generative approaches to rhythm. What you see on screen here is a bunch of these, and we're going to sort of build and go through these and then integrate them into the patch from last video. So if we just quickly look at these first, the most basic thing here is just a metronome. So it'll give you pulse. So here I have the metro, it sends out a bang, and then I'm banging a click so that we can visualize it. So we have visualization for all these different things. So see at 202 beats per second. I can send this bang to my little hi-hat gen object up here. Oh, actually, I want to send it as clicks. Yeah. So this is really sort of one of the most basic built-in blocks for rhythm for me. I tend to not use the transport, so I'm working with the metronome, but just using floats. Next to it is another fairly simple approach to bouncing ball rhythms. So I'm using a curve and then taking snapshots of the curve to increase the metronome speed to go from 500 millisecond to 50 milliseconds. So if we can listen to that, what that sounds like on a hi-hat. And then there's a bunch of other objects here. So almost all of the other ones, with the exception of these sort of using the subdiv and the probabilities, almost all the other ones are actually reworked from this book, Generating Sound and Organizing Time by Graham Wakefield and Gregory Taylor. I recommend it highly. It's a book all about gen. And so everything else is either just taken from or adapted from, built off of the objects that come with that book, or the gen code that comes with that book. Okay, so I'm going to close this up now, and we're going to sort of rebuild everything as a subpatcher in our computer improviser. Okay, so here's our computer improviser, largely unchanged since the last day. We'll take this away for now, so we're starting fresh. Just put a scratch pad on the other screen there. Yeah, so what I've done already is I've preloaded in some guitar harmonics. So we can use these as our rhythmic triggers as we're working. By the way, this patch and all future updates for it will be available on my GitHub, which is, you can find here, and I'll send a link to, or not send a link, but post a link in the description of the video. And TSC is the name of the project. So you see here, TSC Part 5 is what you see on the screen here. So totally available to use. And everything is in a single file there. So these are all referenced within the main patch, and the main patch has the 1_ at the beginning so that it just is always at the top. Okay, so let's get to patching our different rhythmic approaches. Okay, so to do this, I'll make a subpatcher, call it rhythmic, and this is all going to be generative at this stage. So rather than something that is interacting with the live input, and then we will also in a future video make them reactive to the live input by using pulse detection, tempo detection, as well as use the ml.star Markov object to train Markov chain with the analysis of the live inputs, the frequency of the onsets essentially. Okay, so let's just begin with the most basic thing, which is our metronome. And so it takes a 1 to turn on and a 0 to turn off. We'll give it a float in the right inlet here. And you can see if we have it at, let's say 122, it's now 122 milliseconds between each attack. Now it's 591 milliseconds. So already we see, or we need to sort of make a decision about if we want to use milliseconds between attacks, beats per minute, or phaser, sort of always dividing by 1. And I think that beats per minute for me is the most sort of human choice, and so will be the most accessible for users. So I'm going to go ahead and do the basic conversions of BPM to divisions in milliseconds and BPM to phaser, because those are going to be the 3 ways that we drive our rhythms. So for this one here, we want to do BPM to milliseconds. And so for that, we can start with our BPM float. And then we want to do our reverse division of 6. Is it 6? It's 60,000, right? Yeah, 60,000. And that will give us our milliseconds. Okay, so we'll just test that to make sure. So that bug is super annoying. All right, so BPM is 60, should be 100 milliseconds. At 120 should be 50 milliseconds. Great. So we can go ahead and instead of doing this, we can just plug this in like that there. BPM. Great. So now out of the metro, if we give it 116 BPM, there's our 116 BPM from the metro. And now I'll often want to be triggering things as, I want to have the option of triggering things with a bang and triggering things with a click. So we can just simply use the click object for that. Bring in a live.scope object so that we can view it. Great, and so that requires audio to be on because that's an audio object. Okay, so there is our basic metro. So let's build our bouncing ball rhythms next. So I'll comment this, basic metro here. And I'm going to also make a simple test into the main patch. So I'm going to have a receive object here, and I'll just call it tester for now. And I'll put it into the 2-dimensional grid KD tree. So if I give it a list of 2 floats between 0 and 1, then it will trigger that. So for now, or trigger the nearest dot on the grid there. So for now, we don't need to do anything complex there. We just need the random numbers. So for that, I will just do a very simple bit of code here, trigger bang bang, and we'll get 2 random numbers between 0 and 100 and divide them by 100 and make them into floats like so. left input and then right input. Yeah, we'll have a bang there just to test it, to visualize it. And then from here, we simply need a join. And just as a sanity check, let's make sure that works. Very good. And so we'll send this to tester. And so this will trigger a random slice in our corpus. Great. So now, if we connect these up, great. Okay, next, so that's our basic metro. Next, let's do the bouncing ball rhythm. So for that, we will drive that using the metro, using a metro. So we can go ahead and copy this over. This here, call it bouncing ball. And for this, we're going to use the curve object, curve tilde. We're going to make it use floats, and we're going to give it a curve shape. Negative 0.2 has sort of a gradually it sort of moves quickly to toward the sort of slowly slope, or it moves quickly at the beginning, slowly slopes at the end, I believe. And for me, that sort of has a nice musical trajectory. So we're going to use this to control the millisecond input of the metro. So for that, we'll need to convert the audio signal to a data signal. So we'll do snapshot every 10 milliseconds will be about as much fidelity as we'll ever really want there. Filter out duplicates. And then we will also want to use we want to be able to turn it on and off. But because this is audio, it will be sending things constantly. So we could use a gate. We could also use a one bang. I find one bangs to be pretty intuitive. So I'm going to do that. Okay, so here, I'm going to put this here just to sort of check it for now before we hook it up into the metro. But now if we send it a message of 50 milliseconds or 50 to 500, we haven't really defined what it will be yet, but 5,500 over the course of, let's just do 3 seconds. And great. All right, so for this, I think we'll stick with milliseconds for this, at least for now. We could do the conversion, but for whatever reason for the curves, because it's not a steady pulse, it's not really per minute. And I think actually milliseconds gives you a better sense of what it's doing. So let's put that into there. I'm missing a couple. I'm missing the on-off toggle. Instead of the toggle, I'm going to use a 1 and a 0 because I'm going to bang out that those two messages. So 1 bang to 1 to turn it on. And I'm going to flag the end of the curve. It will send a bang when it finishes completing the curve, and that will turn off the metro. So now we'll need a trigger bang bang. And for that, we will want to first begin the curve, and second, open the 1 bang. Is that right? No. Oh yeah. Open the 1 bang first, then send the curve. We will want to also, to avoid double clicks, we don't want to bang it right away, but we want to let the the first number be received by the metro before it bangs out. So in order to do that, we can take that from the change there, and that should work. Let's have a look. Okay, it looks good. Let's see what it sounds like. All right, so I did sort of a reverse bouncing ball there. Let's switch it to go from 500 to 50 in 4 seconds. Great, so sort of a nice speeding up gesture there. Great, so that's our bouncing ball rhythm. Next, let's do using the subdiv tilde metrical probabilities. So for this one, I just want to give a quick shout out. I don't want to mess up the name. So let me just find their YouTube channel. Hold on. Max Subdiv. Philip Meyer, I think. Where is it? Yes, Philip Meyer. I have that name right. So Philip Meyer has been doing a lot of interesting tutorial videos that focus on rhythm and sequencing. So I will also link their channel in the description. I became aware through this channel of the Subdiv object in Max, and it's so shout out to Philip Meyer and thank you for bringing that to my attention. And it's, yeah, his videos are quite interesting. I would recommend them. So the subdiv, we drive with a phaser. So I'll begin with a subdiv tilde here. And for this, you give it the number of subdivisions. So let's say, for now, let's do 8 subdivisions. And then you drive it with a phaser. So let's create the phaser object. And just so we can see what's happening, let me just bring in a few objects for the outputs. So we'll get clicks out of the first output. We'll get the count of what subdivision is being hit in the second outlet as an audio stream, and then the third outlet is a data stream. So if we hook up our phaser in here, and we just give it a, let's give it a 0.25 so that it's not going by too fast. We can see it's counting through 0 to 7, i.e. 8 in total. But what's interesting about this is you can then give probabilities for each of the subdivisions. So for generating rhythm, it can be quite interesting because you have you can basically give the impression of meter, or yeah, just play around with sort of metrical stuff. You see how there is a little bit of a delay between the audio stream and the data stream, which is why often things, if we want to be very precise, are done in the audio stream, if not in gen at the sample level. Okay, so for the probabilities, we would just need to give it a message prob and then a list of our probabilities. So let's say, 0.95, 0.5, 0.8, 0.5, 0.9, 0.8, 0.6, 0.8. 1, 2, 3, 4, 5, 6. Okay, yeah, that's good. So if we give it this message, now we will see that, yeah, if it doesn't meet the threshold, it won't send that. And so it will, the ramp will stop, and also the number will pause. So we could just simply use a change object here if we want to just get bangs. But then of course we could also use the fact that it's counting. We could use a select 0 through 7 object, and then that could be, say, be used to trigger different labels in different parts of the meter, as in sort of different colors here, our labels from our audio analysis, to create interesting patterns. So because it's cumbersome to write all these out, I'm just going to quickly do sprint f. So it should be prob, and then it's just a bunch of floats. So that is ampersand, not ampersand, modulus f. And we want 8 of those. 1, 2, 3, 8. And here we do this. So it's just a pure list without having to have that. And we could also do a prepend prob, and it would work as well. Yeah, let me make sure that that is looking good here. Yep. And it's just sanity check. Good. Okay, so there's our meter. So one thing that I want to do is not have it being driven by a phaser, but driven as BPM. So for that, again, we just need some simple math. So BPM to phaser, we just need to divide by 60. And we should get our conversion. So let's try that. So, and remember that this is for all 8 subdivisions, because we can think of it as bar length. And of course we could do different numbers of subdivisions. So let's say the bar takes 30 beats. Let me just go to this. Yeah, great. So if we're going, if we're thinking them as 2 measures of quarter notes, then for 8 divisions we would want it to be what? I do the math quickly in my head, but like something like around 10, a little under 10, right? Great. So there's another way of generating rhythm there. So we'll call that meter and probabilities there. All right. Next, let's go with ratchets. I believe Philip Meyer also has a ratchets video. We're going to do ours a little differently using gen. So this is one of the objects that was part of this book here, the Generating Sound and Organizing Time, Thinking in Gen Book 1, Graham Wakefield and Gregory Taylor. So I'm just going to go ahead and paste in the code here. So this is something that comes with the book. I don't want to share everything that they've done, but it's very there's lots of sort of useful bits of code that comes with the book, and I recommend it. So here again we have a phaser, so 1 second intervals, and then we have a ratchet. So how many subdivisions, right? So 4 subdivisions within each one, and it changes only when you get to the next one, right? So you see a lag in the changing. So if we hook this up to our rhythm here, this is something that maybe sounds a little bit more obvious with something a bit more percussive than the samples I have in there. So this is a little drum sample, but like a little drum synth. Yeah, it could be interesting to do something like, well, first let's get this as BPM here. drag this down here. It could be interesting to do something like we could also have a metro that is at the same BPM, that is giving you a random number between, let's say 0 and 4. We'll do +1. Or here, let's actually do like 6 and then +2. And that is going to change the number of ratchets. So basically with every beat, we'll get a different number of ratchets. So put that there, turn that on. Oh, of course, I have to give it this. So let's say it's 60 BPM. Oh, sorry, it should be coming from here. Yeah. Great. So, oh, of course the conversion's wrong there. I need to convert from BPM to milliseconds. I was wondering why it was acting all glitchy there. All right, so if we do it that way. Great. So we're getting different subdivisions with every beat. Go ahead and turn that off. Okay, so those are our ratchets. Next, let's add in Euclidean rhythms. So this is slightly adapted by me from the same book. I'll paste it in here. And we can see that it's a little bit more involved. And again, with this, we can give a sense of meter. And we also have sort of 3 different things coming out there. So we have the number of events within the pattern, the length of the pattern, and the start offset of the pattern. So this can all sort of work together really nicely. If we have, especially if we have 3 different timbres to work from. And so just for the sake of testing, I'm going to bring in these 3 little gen synths. These are also very slightly adapted by me from the Wakefield book. Okay, so let's go from here, here, and here. Number of events, let's turn that down. Change the offset. Okay, you get the idea. So the Euclidean rhythms have that sort of nice groove to them, but definitely something that could be usable in the patch. You know, the more active middle one, go ahead and send it to that. Create a kind of a, in this context, a sort of wave of sound mass. And at that speed, you can start to hear the rhythm a bit better. Okay, great. So there's our Euclidean rhythm. Now, there is also, in that same book, there is gen code for all sorts of chaotic attractors. So this one is the Lorenz attractor. for this, you have sort of 3 values that it sends out and moves in sort of a quasi-random way. And so these, yeah, you sort of end up with interesting patterns as a result of this. And I will show you what that sounds like. It's definitely a bit more sort of random sounding because it's not symmetrical or sort of groovy. But this DT variable can be used to make it more or less active. So if we turn it up, turn it down, right? Yeah, so this could be quite interesting. I mean, all the point of all of this is to sort of get a lot of different options for rhythmic generation that we can then build off of and use in the patch. So each one should have sort of a different feel to it so that it doesn't become too predictable. And that you can have sort of different modes, maybe sort of different personal preferences in terms of what you use when you're actually playing with this thing, or maybe like adapting the patch. Okay, so there's a couple of other ones that I think I'll add in, but I don't feel the need to sort of walk through. But a couple of ways in which we can sort of add on to these that I think are interesting is one is using a sieve. So basically a patch that will not let every bang through based on probability. So again, this is done with in a very simple way here in Gen, just using the chance object and gating it. So if we send clicks, right now it's got a 50% chance of going through. So we could, for instance, hook this up if we had a very active third variable here. We could hook this up into the sieve here and make it have like a kind of a low probability of it being let through, and have that be sort of an even more erratic rhythm. Oops. So we can just go straight to here. Yep. Or this could be used as a sieve for, say, the fastest of the Euclidean rhythms. So that is which one here? That is the, oh yeah, but it's down here at that point we can grab it. There you go. Let's give it a higher probability. 0.8. Right, and then we can still give the kicks, maybe here. Make this more active. Right, so it's a sort of modifying our Euclidean rhythm. Great. Okay, so that's our sieve. Another thing that we might want to have is a little bit of variability in the speed by which these things are being driven. So for that, there is this handy patch here, also from the Graham Wakefield book, that gives you normal distribution. So it simply multiplies, and I've changed the numbers here, I think, a little bit from how they had it, so that it now goes between, I think, 0 and 1. But it just multiplies a random value by pi, so you get, and then uses the Poltecar so that you get it sort of mapped in normal distribution. So things will tend to exist more and more, or it's more common for the number to be at 0.5 than anything else. But you get, or is it, oh, hold on. It seems like it's not distributed between 0 and 1, but actually a lower number. So in any case, you do get this distribution of numbers that we can then use for humanization. So if to do this, we could use the change here so that we don't get repeated numbers. We could say make it, so I'm just going to fudge the numbers a little bit. If we go in my -0.4 to get it hovering around 0 rather than around whatever, 0.2 or whatever it is now. Let me see what, hold on, -0.4, what am I, oh right, the change object needs to be told about floats. So I want things to tend to be around 0. All right, it seems to be, let's do -0.3. Okay, that seems generally reasonable. And then so we could use this number. We can maybe make it smaller, maybe divide it by 10. And then finally multiply it by 1. Or rather, sorry, no, we want to add 1. And now we can multiply this number by, say, the BPM. So that it's always around 1, but not exactly, or it's always around what is being told, but not exactly. So for instance, if we just run a metro, yeah, let's just bring this down here. And let's add a multiplication here. We'll get the result here that it actually is. And that to there. And now turn this on. Say it's 120. And let's send our clicks to this. Hold on. I want to do this the other way. So 120, and we could even send this back into here. So it will sort of hover around 120, but give you a bit of humanization. I think I'm able to hear that. That's actually not bad. I would maybe reduce it a little bit. I could divide by a larger number here, for example. Great. So that's how that normal distribution can be handy in improving the rhythm. And I think that's it for now. There are two others. I guess maybe I might as well add them in now. So let me get rid of that. Move this back up here. So here we have smoothed randomness, again adapted from the same book. So if we take this, we get this sort of randomly moving spline, which sends out even bangs from the phaser, but will randomly move between these 6 values here. So one could use a select object in the same way as with the subdiv object, where it's counting through. And so you could sort of count randomly between things here. You could sort of move around in an interesting way there, or this could also be used again for humanization. And it can be used for humanization of rhythm, but it can also be used for humanization of pitch by changing the speed of the playback. Now the last one is one that adds random durations via periods to a pulse. So if we listen to this, sorry. So let's say this is at 6, a lower amount will be more even. It adds a tiny bit of time between because we're adding sort of, the depth is a multiplication of a random value there. And so the higher it is, as it approaches 1, I believe it'll add much more time between each. But at 0.1, it kind of has this nice sort of human feeling to it. Great. Okay, so those are our approaches to rhythm here. From here, we are going to do more reactive rhythm in the next video by doing BPM detection and to control these, as well as create a Markov chain using the ml.star package that's available in Max from Benjamin D. Smith to sort of train a Markov model to generate rhythm. Okay, so that's it for today. Hopefully that was interesting. And once again, I will clean this up and put it on GitHub.